1.645 or something. Okay, so it's a left-tailed test. But now what I want, and this is 4 down the middle, what I would like is a two-sided confidence interval. And so the two-sided confidence interval, I got to tell SAS, in order to get this to be 1.645, SAS has to think that it's running a two-sided test where this is also 0.05, in which case the alpha would be 0.1. That's the only way you can get SAS to use this number as the multiplier in the confidence interval.
Got it. So, okay, got it. So basically, to get SAS to get the appropriate multiplier, even though we're doing a one-sided test, for it to do the confidence interval, it has to treat it as if it were a two-sided test with 0.05 on each side, and that's why there's 0.1 in your proc GLM as your alpha.
That's right.
Okay.
That's right. The only reason why it's there, notice that I could say sides equals 2 in there, in which case it would split that 0.05 into each tail, but sides equals 2 is the default, so you don't see sides equals 2 in there. You just see the alpha 0.1. So I imagine that's confusing to some because we haven't seen that in a while. But so let me do another example. Let me finish. Could we have done side equal L and then just made alpha equal 0.05 so that the 0.05 would have been constant with the t-value? You could, but then you would have gotten a one-sided confidence interval, which is fine. It's just you're getting my subjective opinion on it. I like for my confidence intervals to be plausible values of the mean.
Okay.
And when you have plausible values of the mean given the data, and if you have a one-sided confidence interval that goes from negative infinity all the way up to here, then if my sample mean is, let's say I got over here in my x bar. Let's say x bar equals 3. Let me do this all over again. Let's write this the way it should be. So this is 4. This is t. This number here is negative 1.645. And let's say for whatever reason, based on the standard deviation, this right here was 3, and that was my x bar. So x bar equals 3. And what ends up happening, this has some t-score that's less than negative 1.645 when I found it, but when I end up doing my confidence interval is going to be x bar plus or minus 1.645 times the standard error of x bar. And let's say that turns out to be, actually I can take this out the SAS and do this, but let's say that turns out to be, if this is over here, I want this to be, let's say that this is, hang on a second, 2.5 to 3.5. Let's say that that's my 90. In this case, that would be a 90% confidence interval because there's 0.05 over here and 0.05 over here. And so this would be a 90% confidence interval for mu. And what that's saying is that the plausible values, if 3 is my mean, the plausible values for mu is between 2.5 and 3.5.
Got it.
And if I use a different multiplier here, this thing might contain 4. So it might reject here, but contain 4. And we don't want that to happen. If it's in the rejection region, I don't want my confidence interval to contain it. And if you set it up like this, where this is the critical value to the test, and this is the multiplier to the confidence interval, they'll never overlap. I'll never reject here and have 4 here. It'll always agree.
Got it. So if I've understood you, then in other words, in order to get, you have to do the two-sided test. If you're going to get that mu equal 4 to ever have an acceptance region, and the acceptance region is defined that everything that's not the rejection region, you need to do a two-sided test.
Sure. I guess I would rephrase that as the fail to reject region,
Yes.
because we don't want to accept.
We never accept. Yeah.
That's right. So, but just to give everybody kind of a clue as to what we're talking about there, or a reminder, let's say that I'm doing this. Let's say I'm doing HO mu equals 10 versus HA mu greater than 10. And let's say that my alpha is 0.01. So go ahead and draw that test. In fact, we'll do this all together. This will be perfect. And this is actually really important stuff. So if you drew that test, that's 10. It's a right-tailed test, so this is over here. But this time, that's 0.01. And let's say that my sample statistics were X bar equals, in fact, let's do this. So, well, here, I'll just do it on the calculator. Should we do it in SAS? Let's do it in SAS. Let's do it in SAS so we can see it. Maybe. Oh, good. Unbelievable. Whatever. Oh, yeah. I'm trying to share my screen. Sorry. Is it doing something on your end? I don't know what it's doing. Maybe I ate up too much memory.
Oh, you're running SAS local?
I am. So I was going to run a applications, process, CPU, Adobe Connect. Hang on one second. If worse comes to worse, I know what I'll do. Yeah, SAS is eating up all my memory, but I need to run it. So that's not going to work.
Well, there's the other choices. We could do it online, and you tell us what to do, and we share our screen.
Ooh, I like that. I've never done that before.
Let's try it.
You want to drive it, Mac?
Sure. Let me see if I can share my screen. And then I'll open up SAS, and you lead the way and see what we need to do here.
Okay, well,
I shouldn't have any problems. I have 16 gigs worth of RAM, and I'm doing it on the cloud, so it shouldn't suck up any of my memory.
Yeah, well, that's good. I can't seem to get, I don't know if you guys can see this screen or not. I can't seem to get it.
Oh, here we go. We say make presenter Max. There we go. And then now I got to see how I share up my screen. There we go. I'm going to say share my screen. That works. And let's see, I'll share the screen where you guys are not, and I'll go like this, and I'll open SAS on that screen. Can you guys see my screen?
I can only see my screen.
I can see your screen.
Okay. You see the word doc?
Yes.
Awesome. Now let me open up SAS here, and then I'll listen to the professor and follow directions. All right.
Well,
so
it's kind of I can see it, Max, because I'm going to have to. We're going to do this. This is what I'd like you to do. I guess if I leave, you probably can't see it. Maybe you can see each other if I leave. I'd love for you to create a data set with, try to create a data set with 7 to 10 values with a mean of 10 and whatever the standard deviation turns out to be. Try to make the standard deviation small, like 1 or 2. So
okay, 7 to 10 values, mean of 10, standard deviation 1 or 2.
That's right.
Okay. Can everybody else see my screen?
You're good, yes.
Is there anybody other than the professor who can't see my screen?
Yes.
All right, I'm starting SAS right now.
All right, and I'm logging in on the other side of my machine.
All right, we got SAS open here. All right, guys.
All right.
Let's see. So we need a mean of 10. So and we need 7 values. So
Okay. So this looks great. Yeah. So just plot some values in there. Yeah, this would be great. So.
Professor, can you see my screen or no?
I can. Yeah, I logged in a different way.
Oh, cool. So I'm going to add some values here. So we have 15. So we have 25 and 35. That's 70, 80, 90, 100. I'll go with that. We'll see what happens. And if I go proc means, right, on data equals my data. And then I think I just run and see what happens here.
Sounds good. Whatever.
Then we could just change the values to adjust it. So I got a means of 12. I have a standard deviation of 3. I think my standard deviation is bigger than you want it to be. My
That's
mean's
fine.
a little bigger. Okay. All right, where do we
We're
go
good.
from here, Professor?
This is great. Okay, so let's say that we wanted to run this test with that. So we said, oh, hang on. I got to get my, okay, if I'm up there. So I want to run this test up here with that data. And it looks like the mean was 12, right? The sample mean was 12, which is bigger than 10. But the question is it significantly bigger than 10? And so what I'd like to do is run a hypothesis test on it right now. So you're going to run a proc t-test, and I want to know if 12 is over here or if it's over there. And then I would like to make a confidence interval that will agree with it.
All right, so I'm going to say proc t-test is my data, and then over here, let's see. Now, are we doing a right-sided test or left-sided? Because
Good. Right-sided, so how do you do that?
Say that again, Professor. My phone cut out for a second.
So would that be right or left? Or up or
lower?
lower?
It should be a right side if it's greater than. It should be a left side if it's lower. But I didn't hear what you said.
But if it's greater than, then it should be right.
It should be upper. God bless you.
So that's up. Yes.
And then alpha equal 0.05?
So let's leave alpha. We'll leave alpha out right this second. Actually, that's okay. You got it on there. Oh, shoot. Everything's delayed. Go ahead and put it alpha 0.01.
You got it.
Okay. And we'll fix that here in a little bit. So
all right.
Now we also need, so this is a key. Whoops. A key is going to be that right now you're going to get this astronomical t statistic, 8.65, because we're not testing this null hypothesis, right? We didn't tell it 10. It's testing it equal to 0. And it's saying, 12 is significantly different than 0. So you want to put in H0. Yeah, there you go. In that line. H0 equals whatever.
10?
Equals 10. That's right. Run that guy.
There we got 0.051. It's on the verge.
Yeah, wow, you couldn't have picked any better data. Nice work, Max. So this is 1.92. So what this is saying is, right, that's bigger than 0.05 actually, but our alpha was 0.01. So are we going to reject or fail to reject here?
Well, it depends. What's our alpha? If our alpha is 0.0, if it's 0.05, we're supposed to reject. But darn, it's so close.
Well, let's just stop there real quick. If it's 0.05, what we're saying is, right, it's alpha. What it's 0.05 is saying, if it's less than 0.05, then that's too rare for us. If our p-value, the probability we observe something as extreme or more extreme than what was observed, given that mu is 10, if it's less than 5, that happens too rare, and I'll reject. But this one's actually bigger than 0.05.
We're gonna fail to reject.
So at the alpha 0.05 level, we'll fail to reject, and our alpha is actually 0.01. So what are we going to do here?
If our alpha is 0.01, a fortiori, we're going to fail to reject.
Right. We're really going to fail to reject.
Yeah.
So so good. So here we're going to fail to reject. So what we're saying is that 12 is probably in here, or not even probably, I'll just estimate that 12 is in there somewhere. And that this t statistic right here is that 1.92.
Mm-hmm.
Great. So if we fail to reject mu equals 10, should that be in our confidence interval? Should mu equals 10 be a plausible value of the mean if I fail to reject it?
Yes, it should be in the confidence if we fail to reject it.
It definitely should. And so since we have run the one-sided test, notice that it's giving us a 90, if you look on Max's output there, it gives us a 99% confidence interval from 8.843 to infinity. So it's going a little bit less than 12 all the way to infinity. But that's your one-sided test. And notice that one-sided confidence interval contains 10, which is why we failed to reject. So what I think personally, and the guy that I learned it from, and I think it just makes more sense in practice, is to give people, if they get a true mean of 12, if their true value is a 12, their sample mean, not their true value. If their sample mean is a 12, I want to know what the plausible values are. And I'm pretty sure a plausible value, if my mean is 12, a plausible value isn't 13 million, even though that's in the confidence interval.
Got it. And I see what you're saying. That's why over here you would have done, then one would have gone like this. Sides equal 2. Alpha would have been 0.05 to cover it, and then this would give me a positive, negative, and I won't end up with infinity as a value. Oops, hold up, I screwed up.
So that's right. So you definitely won't end up with infinity as a value. So go ahead and run that.
What did I do wrong? It died on me for a second. Sided equals 2.
You didn't highlight the P when you highlighted it.
Yeah. Okay. I missed a letter. Yeah. Thank you, guys.
Yeah, good.
We're quick to jump on you when you do something wrong.
That's all right.
Believe me, I know the feeling.
Listen, at 53 years of age, you've made so many mistakes. What's one more,
Right, yeah, you just kind of roll with the punches.
I know exactly what you're saying. That's why I made the joke.
All right. So Professor, you're saying that here the 9.2 to 16 would be more meaningful than 8 point something to infinity, because if it is the case that the real min is 12, that's meaningful. Where the other one, for me, would have been meaningless, because 2,593,000,000,000 doesn't really mean much.
That's right. That's right. Now this guy here though is a 90. So that's perfect. This is a 95% confidence interval, though. Notice right now it agrees. We failed to reject 10. 10 is in the interval. And it's as simple as that. We failed to reject it, so it's plausible. But we want that to happen every single time. And what I'd like to do is have things outside the interval, anything outside the interval, then reject. And at the alpha 0.01 level right now, that's not going to happen. So let me just cut to the chase here real quick, and we'll kind of just play with the numbers, just to show the sensitivity of it. But yeah, if you go back to the code.
Oops, sorry. I could make if I make mu something that other than 10, something at maybe 13, 14, it should fail to reject. I mean, it should reject because it's outside the confidence interval.
Sure, except just so we can get to some other questions, but do me a favor real quick, and let's find the confidence interval that will always agree with it. And that confidence interval, notice this one was an alpha 0.05 left tail test, so I just doubled it to get the corresponding two-sided confidence interval. So I made that 0.1, which was a 90% confidence interval. Over here, this is alpha 0.01, so all I'm going to do is mirror that 0.01 over here. And if I have 0.01 over here and 0.01 over here, I'll have a 98% confidence interval. A 98% confidence interval corresponds with an alpha 0.01 test, right-sided test. An alpha 0.01 right-sided test corresponds with a 98% confidence interval. So if you change that alpha to 0.02,
Yep.
So yeah, change that alpha to 0.02 and then run it, and we'll learn something here. Remember that our alpha is 0.01. And let's write this down. So this confidence interval that he gets out is 8.18 to 17.53. 8.18 to 17.53. That is our 98% confidence interval for this data. Given, so let's think what that means. Given that our sample mean that we found was 12 something, 12.8, given that our sample mean, X bar, was 12.8, the plausible values for the mean are 18.18 to 17.53. So at the alpha 0.01 level of significance, I should be able to put in a 16 because 16 is plausible. I should be able to put a 16 in there, and it'll fail to reject at the alpha 0.01 level. So go on back to the code and put in 16 instead of 10. And just kind of take a deep breath and say, since it's in the interval, it should agree. If I make that 10 a 16 now, it should still fail to reject.
It does, because it's 0.07.
Because it's 0.07. So let me ask you this. What if I put 17 in there? Is 17 a plausible value? And if I put that in there, should it reject or fail to reject?
It should fail to reject, because at least at this confidence interval, because 17.53 was the upper value of that 98% confidence. I'd need 18, something greater than 17.53 and something less than 8.18 for it to
awesome.
To reject.
But just for the sake of practice, let's go ahead and cut to the chase that you just alluded to. Let's put in 17.5. And everybody think put in 17.5, but don't run it yet. Everybody think, is your p-value going to be just bigger than 0.01 or just smaller than 0.01?
The p-value should be bigger.
That's right,
just
because
bigger.
We're going to, at 17.5, we should still fail to reject. But we're on the border. We're getting close.
Yep.
So that should be getting close to 0.01. So go ahead and run it.
Yeah, look at that.
There we go, 0.0205. It's actually a little bigger than I thought it would be. So now let's go to, that was our value, so let's go to 17.6. Let's go to the other side. Let's go to the just outside our confidence interval. 17.6, and we'll see if this...
That we reject it at that point. We reject it.
That's
sure,
right.
There we go.
Oh, hold on a second.
Look at that chart on the border.
17, well, hold on. That shouldn't have happened. Well, I hate when so that's alpha 0.01.
At a 98% confidence interval.
Oh. Okay. Yeah. Darn it. Okay. So this is the other thing we got to remember is remember that he's running a two-sided test right now. Right? You're still running that two-sided test.
I am.
So go back and right now make that a one-sided test and run it.
Okay.
Just make that a one-sided test. Yeah, upper.
There we go.
Run that because it's multiplying the p-value times 2. So,
oh, look at that. Yep.
Well, that's
0.9906.
Yeah, that's way too.
That's huge.
That's way too big. At the alpha 0.01. Yeah, because that's 19.
I got an alpha 0.02. I should have made that alpha 0.01 when I went to one-sided, shouldn't I? I left it at 0.02.
No. So what this, let me draw it out. This should be 17. This is 12, and it's still running a right-tailed test. That's right. So if we're running a right-tailed test, and we're testing 10, yeah, I'm sorry. We should have been going the other way. That's the downside of this. Sorry, Max. Test the other end of that, because what we're doing is running a right-tailed test, and we're trying to say, hey, these are the plausible values of the mean. We saw a 12. We saw a 12. So if the plausible values of the mean are between here and here, these will of course fail to reject, because if we're testing, if mean is, we want to test here 8.18, test 8. So just put an 8 in there.
There we go.
Yeah,
got it.
Just like that. Put that 8 in there, and that should be, that's the one we're testing.
There you
So
go.
that's the 0.0086. The closer you get to 8, that's the trouble with the two-sided, is that on the one side, it's always going to fail to reject. So at the 8.18, this one will always agree on this side. And if you flipped it to the left side, it'll always agree on this side. But that's the idea. The idea is that if you want a confidence interval that will always agree with your right-tailed test, if this is 0.03, if your alpha is 0.03, the confidence interval that will always agree with it is that's a 94% confidence interval. And the way you're going to get that 94% confidence interval is by telling SAS proc t-test data equals whatever, alpha equals 0.06. You'll just, to get that two-sided confidence interval that'll always agree with it, you'll put in, if it's a one-sided test, if this is an alpha 0.03 test, you're going to put you're going to put the 0.03 over here, you're going to double it on the other side, that's an alpha 0.06 if it's a two-sided test, and you're running a 94% confidence interval that will always agree. But if on a test, I'm not sure this one's on there. If on a test I just ask for a confidence interval, you can give me the two-sided confidence interval, which would be great, or you can give me the one-sided confidence interval that just comes out of SAS. So you don't have to worry about this so much. But that's where that came from, was on the test there we had, what did I have? I had an alpha 0.05 one-sided test, and then I wanted a two-sided confidence interval, so I doubled the 0.05 onto both sides, that's alpha 0.1, and then you run that confidence interval, and you get a confidence interval of plausible values that will always reject, will always not contain it when you reject it, and always will contain it when you do, when you fail to reject.
So if you were, so I'm going to generalize then. So when you're doing a one-sided test here, if you had a t-value of x, then when you're entered as your alpha in your proc GLM, it's going to be 2x.
2 alpha. For a one-sided test,
alpha. Yeah.
For a one-sided test, you have alpha, then 2 alpha, because it's going to, because two-sided test is going to split it into both sides.
Okay.
So,
and if it were a two-sided test as opposed to a one-sided test, then you'd use the same alpha for both.
that's right. That's exactly
Okay.
right. If it's a two-sided
cool.
test, it's already split, and it'll always agree.
Okay.
If it's a two-sided test, those things will always, and we could show.
Hey guys, and sorry about taking so much time. I looked at it and I said, okay, why are we using 0.05 here and using 0.1 on proc GLM? So I thought there was a problem there.
That's my fault, because my example got turned around backwards. That's why it took so long. But it is good, and it would be nice if everybody just plays around with that. Create your own data. and then play around with the confidence intervals and make sure that if it rejects, that it's not in the interval, and if it fails to reject, that it is in the interval. And you'll see that those borders, anything in the interval just in there will barely fail to reject, and anything just outside of it will barely reject. So it's always good to give those kind of confidence intervals. But again, for the test tomorrow or test on Saturday, if you're asked for a confidence interval, it'd be nice to have a two-sided. But if you just give me a one-sided, it'll be fine.
What exactly will we be?
Go ahead.
What exactly are we allowed to use for the midterm on Saturday?
You can use anything except for somebody else. And
Okay.
somebody else includes texting or chat rooms or, everybody knows what I mean. Just anything that involves communicating with another live human being. Or
you're limited to the trendy stupidity, me, myself, and I.
That's right. Hey, that's it. No Siri. Actually, you could use Siri. Maybe no Alexa or whatever that is. She's too smart. But you get what I mean. It's just you sitting there on the computer. You can use your homework. You can use your PowerPoint. You can use the internet. You just can't use Facebook or chat rooms or anything like that. But you can use anything that's out there. Now, I will say this. You only have 3 hours, which is plenty of time. Again, we've talked about this a little bit before. You only have 3 hours, which is plenty of time if you kind of know, if you've studied as if you don't have any materials. So the more I think about it, a lot of times on campus I get this, why do I have to memorize anything? I get this all the time from the undergrads. Why do I have to memorize anything? Because I've got a book that has it right here. And I'll go, you know what, you're right. But I'm not willing to wait 20 minutes for you to give me the answer. And that's what it takes. If somebody doesn't know anything, then it's impossible to synergize 2 or 3 pieces of information because you can only load one thing in at a time. If you have all those in your head and you're able to pull from them quick, then you can put thoughts together. If you're like me, I have a thought, I'm like, that's great, and then it's gone. I've got to be able to synergize it and make it stick with some other information. And the only way I know to do that is to keep it in your head. So the how I would study for it, or continue to study for it, hopefully, is go through those homeworks, study for it like you don't have any materials. And then you will have the materials on the test. You see a problem, and you're like, I either know how to do it, I'm so confident in it that I really don't need to look at anything, or, that's right, I just looked at it. It's from homework 7. Or, okay, that's it's no homework 7. We're in homework 7. That's from homework 3. And we're, that's in PowerPoint 3. That's from chapter 3. Oh, that's a non-parametric test. That's from chapter 4. Oh, we just did that in Unit 6. That's a contrast. Let me go look up that code. Maybe I can find an example real quick if I'm not sure, but I know I don't have a lot of time. But a good thing I just looked at it yesterday, and it's kind of in my mind, so I'm just reminding myself instead of trying to learn it. That's my only disclaimer, is that the time limit on the test is the bound that creates hopefully the motivation to really study this and have it on the front of our mind and not just know where the materials are or have to hunt around for them. Because you won't finish if you have to, not you, but a student won't finish if they have to search around too much for the answer.
So is it going to be structured like the practice test then?
Yep. Actually, yep. I try not to write it before the review because then I inadvertently give things away. But I've already written it, and I think I might amend it a little bit here and there. But it's got 2 analysis questions. It's got right now it's got 6 or 7 multiple choice, but they're those kind of multiple choice that are like grouped up true-false questions, kind of like you saw in there. So like one question might say circle all that's true. So I kind of count that as more than one question.
Okay.
But it's if you took the practice exam, I've got a bonus on there. So if you do have time to finish, it always breaks my heart when it might just be an undergrad thing, but when I'm teaching on campus and I've had this where like somebody's like really mad at me. They're like, I didn't have enough time to finish. And then I look at their test and they were working on the bonus. And I was like, there's two types of students. There's some that work on the bonus before they're finishing the test. I'd never recommend that. And then the other one that is just, I kind of admire it on the end level. I'm just sad that I got disappointed, is that the 3 hours doesn't include the time to do the bonus. If you're particularly quick and you got through it and you want some extra challenge, that's what the bonus is for. But by no means have I planned 3 hours for everyone to finish the bonus. On average, I would think that people should finish this exam on average by 2 hours and 15 minutes, plus or minus 45. It's probably more plus than minus 45. So you should finish between 2 and 3 hours. If you're like me, I wouldn't turn it in early. Go ahead, sorry.
So I was going to say, for those who don't have a statistics background, is there any way we can extend the time limit from 3 hours to something else?
Well, you do have a stats background now. You've had 7 units of
That's a 6 units of stats background, right?
I hate to bring it to you.
No, actually, I was wondering because from the previous batch, I think they had like a couple of days to finish it up, like a homework thing. So I thought maybe we can get at least 24 hours to do that.
Yeah, we're just we're changing it up. At one time they had like 5 days to finish it. And at one time, when I first started, we opened it, and 24 hours later, you had to turn it in. Just to be quite frank, there's two things. We had some issues with breaches of the honor code, just because it's out there. So we're not. I'm just being straight up. Like that's one thing that we're trying to do here. Another thing is accreditation, which is really the main thing, which is really good for you. It's good for us, good for the school, which is good for you and everybody. The accreditation wants to know that there are safeguards in place to make sure that everyone is doing their own work, and basically that's it. And unfortunately, we have to deal with that. But that's
Professor, I'd like to steer us back to some questions since the time's limited. On page number 2 of the quiz, I see that estimates used in the ProcGLM. Why estimate as opposed to contrast? And why would one use contrast versus estimate on a ProcGLM?
Okay, let me see if I can get my share my screen to work. But with estimate, if I'm going to make a confidence interval?
No. It says estimate or contrast, but it was never explained what's the difference between the two. And one would use one with versus another one. We do linear combinations.
Right. So estimate gives you the estimate. So contrast is going to give you the p-value and say whether or not those two combinations of means or whatever your contrast was is significantly different. Estimate is going to give you the same information, but it's going to give you the actual estimate of that difference. So in my opinion, it gives you more information. So if you're looking at, say, the handicap example, if you're looking at a contrast between the average of amputee and crutches and the average of wheelchair and none, if you're looking for the difference in the average of those two means, contrast is going to give you a p-value that either rejects and says they are significantly different, or fails to reject and says there's not enough evidence to say that they're significantly different. Mm-hmm. Estimate is going to say a p-value also, that same information, except it's also going to give you the estimate of how far apart they are, which is this average minus this average. It's going to give you G, and it's going to give you a standard error for that. Right? That's what estimate gives you. It gives you the estimate, the standard error, and the p-value. From that, you could build a confidence interval if you wanted to, whereas contrast is just going to give you the sum of squared residuals from the F test that it ran, which will give you the same p-value, but it's not going to give you the information you need to really go to the next step. You can ask SAS to give that to you too, but
are we going to have any manual problems that we have to do, or is everything going to be SAS? And the reason I ask is there's some tests that take a long time. So if I'm going to do a rank sum test, very manual, very, if I'm going to do a G, a gamma, that's going to take some time because I have to get, I have to figure out and do the confidence interval for gamma and figure out the sum of square error for gamma as well. Is that something that we would be using SAS for, or are we going to spend time actually doing manual work?
Good question. So two things. I would know how to do both, definitely. And if it is manual on the test, then of course that has been built into the time of how long we think it should take in part of that 3 hours. So so it's certainly fair game. It's possible.
Okay.
I know it doesn't. I get all. So yeah, I know you just want to.
It's just a matter of preparation because if the only thing we're going to do is SAS work, then I'm not going to sit there bothering going over rank sum and going over a whole bunch of manual stuff. If it's the case that's the possibility that there's going to be manual work, then all that tedious manual work is stuff that I need to make sure that I have, pool standard deviation equations and everything else, right in front of me so I could get to it quickly.
Yeah. So I would, great. What we'd love, I just want to say this one little public service announcement just for my own benefit, I guess, is we have been through Unit 1, 2, 3, 4, 5, 6, and I and the other instructors, but since it's you and us, like me, I'm really proud of you guys. And so I'm sure this isn't, good to hear from a student's point of view before the test, but I look at us as a group and you individually as statistical Ferraris that we have built. And what do you do with a Ferrari? You don't drive it around the block and be all nice to it. You take it out there and you get it on the highway and you let it rip and you see what it can do and you push its limits a little bit. And so so that's what I view as an exam time. I get all, I get all kind of, I'm a coach too, so I feel like it's the day before the playoffs. It's the big game. So we've been practicing. We've had successes, we've had failures, we've learned from the failures, we've gotten better, and we're to the point where we're now going to play the game. And the only problem is that unlike coaching, I'm the other side too, which kind of sucks for me. But I have to make the test, so I have to make it so that it's challenging enough to really challenge your Ferrari-ness, but then, and not too easy, so that everybody's bored with it at the end. So so that being said, I've got to find this fine line. I'm really stoked that I'd love for you guys to come out of this program, boom, kind of seeing it. Just see, you can see this rank sum test. You can see the gamma and the G, and you can see the SE of the G. And after you do that, you're going to take G and divide it by the SE of G, because that's what a t-statistic is. It's an estimate divided by the standard error. And then, of course, from there, I could go look it up on a t-chart or on an online t-calculator, find the p-value, and make my decision. So so that being said, I want to show you this, and we've got, obviously we have time to answer more questions, but I think this might narrow it down a little bit. So here's a checklist that it says may not be exhaustive just in case there's something on the exam, but this should be 90% of, you should definitely know the things on this checklist. So the first one is be able to construct 1 and 2 sample hypothesis tests and confidence intervals based on the T and normal distributions. You should be able to do that by hand and by proc t-test like Max just did. So that's one. He did the 1 sample, know how to do the 1 and 2 sample. That is fundamental. Number 2, know the assumptions of those tests and be able to perform a log transformation and know how to interpret the results from a t-test performed on that data. So we did some with log transformations, and we're going to do a lot more in the future. So, know why we perform a log transformation, know how to interpret. Remember, it's the interpretation of the median, the ratio of the medians, rather than the mean. So know why and know how to interpret it. Of course, be able to define a p-value. So important. Know the concept of pooling the standard deviation and why we do it, right? That's fundamental and will continue to be fundamental when we hit regression. So remember, under the ANOVA, right, going back to the ANOVA, or let's just go back to a two-sample t-test. The assumption is that those two groups have the same standard deviation. And if we can make that assumption, then we use the pooled t-test. It says that in the PROC t-test. What does pooled mean? It means that if I've got two groups and they have the same standard deviation, why not use the sample standard deviation from each, pool them together, and get a better estimate of that common standard deviation? Now, the flip side of that is if we don't have that assumption, if we look at those histograms and box plots and we're like, oh, I think there's visual evidence against that, remember, we can still run Welch's ANOVA. But in Welch's ANOVA, we do not pool the standard deviations because we don't have that assumption. And that's where the degrees of freedom take a hit. To expand on that one step further, is we expanded that to the ANOVA, not the two-sample t-test, but an ANOVA, an analysis of variance, where we can now compare 3, 4, 5, 6 multiple groups, means. I can compare mean 1 to mean 6, mean 1, 2, 3, 4, 5, 6, all at the same time. If I assume that all 6 groups have the same standard deviation, why not pool S1, S2, S3, S4, S5, S6 and get a better estimate of that common standard deviation? And when we do that, we increase our degrees of freedom in that sum of squared residual, in that sum of squared error, which makes our test more powerful. So I recorded this, so I think maybe if you wanted to study between now and then, you could go back and just or fast forward to this part. This might be a good one because that's stuff you definitely want to know. Be able to conduct a paired t-test and know when to use it. So remember, we also looked at paired data. And remember, the paired t-test is really a one-sample t-test on the differences. So this was our only real look at dependent data. And so how did we get dependent data? The assumption is that they're independent. How did we get those dependent pairs to be independent? We subtracted them. We took a summary statistic of both. We turned 2 values into 1 by subtracting them. And then we looked at the distribution of those for the t-test. And then, so I encourage you to look over that. And then also the non-parametric version of that was the signed and signed rank test. Another question might be, do we need to know how to do the signed and signed rank test by hand and know how to do a t-test by hand? That is expected to know how to do that. What I would do, this is editorializing, is to just know, have done it a couple of times. You don't have to have it memorized, but have done it a couple of times before the test so that, including the rank sum test, so that you know where to go, or maybe have a sample problem sitting right there. Have a rank sum test, have a t-test by hand, that would be great. Be 4 things. It'd be great practice. It'd be a great resource to have later. And it'll probably help you just memorize it by having done that, just to have a quick reference guide. And I think that's kind of what Max was talking about there too. So after that, be able to conduct a rank sum test and interpret the results by hand and in SAS. So, know how, again, by hand and in SAS. Remember that the results are on the difference. It's a non-parametric test, the difference of the medians, not the difference of the means, really the difference of distribution, but the medians are fine. Be able to conduct an ANOVA. Let's see here. Yeah, the ANOVA, you can assume I'm not going to have you conduct an ANOVA by hand, seeing as though we never really did that. So I think I have extra sum of squares test on there. Yeah, sorry, know every cell of the ANOVA table. Know every cell of the ANOVA table and how to get it. Be able to conduct ANOVA, be able to interpret the results, and be able to conduct an extra sum of squares test. This part you may have to do by hand. Right, the extra sum of squares test. That's where we have a reduced model and a full model. We get the individual ANOVA tables for each, but only to get the sum of squared residuals and the degrees of freedom off of each of them. And then put those into a build your own ANOVA or an extra sum of squares test, your own ANOVA table, and then get the p-value from that.
Those will take you from the standard error of both of them, right? Because there's M, E, and T. I believe we get it from E of both.
Yeah, from the error of both. The sum of squared
Yep.
error. But
Yep,
not the,
and then, yep.
That's right. There's an example in the PowerPoint slides that should be Unit 5 of the archaeological dig, where I had 4 sites. We had 4 sites, and they were measuring the depth of the artifacts found at each of those 4 sites. And that's where we compared. This is what we talked about a lot last time. mu1 to mu4, mu2 to mu3, and then an average of both of those. So, so there's that. That's kind of actually combined with a contrast as well. Know about Welch's t-test and the ANOVA. Welch's ANOVA and Welch's t-test. Those are robust to the standard deviation assumption. Very, very good tests and very widely used. Know how to do those in both SAS and in, actually, yeah, you know how to do those both by, well, let's see here. The Welch's t-test, yeah, the Welch's t-test, I won't ask you to do that by hand, but I might ask you to write it out in a 6-step format. So to write your null and alternative hypothesis, find the critical value, get the test statistic from SAS for the Welch's t-test. Very easy, just get the t statistic from that Welch's row, and then get the p-value also from proc t-test, and then make a decision, reject or fail to reject, and then write the conclusion. And then you may be also, I don't know if I have this on here or not, I'm sure I do, know how to find the scope. Remember the scope. So is it a random sample? Can I generalize to the population? And totally independent of that, is it a randomized experiment or observational study? If it's a randomized experiment, I can draw causation from a 2-sample test if I reject. And if it's observational study, I can only draw an association in a 2-sample test if I reject. If you fail to reject, it's a moot point. Right? If you fail to reject, there's no evidence of a difference, thus there's no evidence of a cause or an association. Cool. So know about the F-test and the BF test for equal standard deviations. So the F-test was the test for equal variance or equal standard deviation. Remember that its assumption was that the 2 groups you're testing are both normal. It is not robust, and under any sample sizes, it is not robust to violations of that assumption. Where the Brown-Forsythe test is. The Brown-Forsythe test uses the median instead of the mean to look at spread. So the null hypothesis is here that the variances are equal. The alternative is that the variances are different, or standard deviation is equal, or standard deviation is different. The null is that they're the same. So if I reject, the evidence is that they're different. If I fail to reject, there's not enough evidence to say that they're different. I like to use the BF test, but definitely know the assumptions of the F test. The assumption is that it is not robust to this assumption that the equal standard, that both distributions are normal. And the central limit theorem for the F test of equal variance is not robust to that. Look at that. Know the assumptions of both tests. Know how to interpret the results of both tests. We just went over that. Know how to provide a scope of inference. Great. That's that 4 square. I think it's on page 9 or 6 or something. It's on one of those 2. Go back to Unit 1. Super important. Randomized experiment versus observational study, and random sample versus not a random sample. Understand the concept of confounding variable. So that goes back to why we can draw causation from a randomized experiment, right? Because in a randomized experiment, theoretically, we've scrambled all those possible confounding variables into both groups. And the only thing that's consistently the same between both of those groups is what it is that we've randomized on, whatever the treatment is. So that's the idea of a confounding variable. We're going to get more into that in regression. I can't wait to get on the other side of Unit 8. But we want to make sure we have this in stone going through it. Know how to read and interpret SAS code for all the above tests. So that's kind of the disclaimer there on finding all of that. Where is know about type 1 and type 2 error and power. And I don't have it on here, but and definitely know the latest stuff that we've done is multiple comparisons and contrasts. So I'll actually post this. I'll post this for you, but so multiple comparisons, and we'll say Bonferroni, Tukey Kramer, Danette. I'd say you can probably stop there. We did study the Sheffy, but you just have to know that that is a version. I won't ask you to make a Sheffy comparison. We'll study that more when we hit regression, but it's important to know that that's what that's associated with. So multiple comparisons, contrasts, why we run them, and how to run them for compound, what I call a compound hypothesis test. Compound hypothesis tests. And that means linear combinations of group means. So again, I'll post this out there so you don't have to look at it off of here, but and that, if you are comfortable with that, and how are you going to get comfortable? You know how you study by now, but I wouldn't be comfortable until I had done an example, at least one example of each of these recently. And if I kind of kept those examples on file, it should be, it shouldn't be too tough. Shouldn't be too tough a test. But a good measure of that would be the practice test. There's some overlap between the practice test and this test, and there's a lot of non-overlap. So there's that. I see a question here, maybe. Scope of inference is on page 9. Great. Thanks, Robert. So that is that. I think that everything on the test, some of these are a little general, but I think everything on the test should be traceable to something on this list. So maybe that makes you feel a little better, or there's a big list, so hopefully it doesn't overwhelm anybody. But it's all things we've gone over, and if you have this stuff down in your head, I'm confident I can sign off and feel really good of you guys going into Unit 8 and beyond. And of course, that just means being able to apply this outside of class and into 6372 and beyond. So, okay, thanks for letting me go off on that. More questions?
Hey, Bhivan, this is Ramesh. Since it looks like we still have some time, can you please quickly go over the solution for like analysis number 2, analysis question 2 for the practice test, the Kruskal-Wallis test and all? And also, if you don't mind, can you post the code for that solution?
Yeah, so I got your email on that, and so I was like, okay, we'll just do it in this live session. So I'm glad you brought that up.
Thank you.
So, good. So where is the practice test? Hang on a second. Maybe it's over here. Practice midterm. Okay. So let's see here. The question was, can you guys see? I think you can. Can you see my Word document here?
No, we're looking at your face.
Oh, good. Okay. Thank you. So let's do this, because I forgot to do that. Share screen. Share screen. Okay, can you, oh no. Share screen. Can you see it now?
Yes.
Yes, we see.
Okay, good. Okay, so there is analysis question 2. We've got this Harvard study fed 38 randomly chosen female mice different doses of red dye number 40 and recorded the time to death in weeks. To decide which mouse receives the treatment, a random number from 1 to 4 is drawn for each mouse. The mouse receives the treatment based on this number. So there's four groups. Control group, low dosage, medium dosage, high dosage. So dosage and time of death are shown in the data file red 40. Test the claim that there are any differences in location, mean or median, between the 4 groups. Perform a complete analysis. Okay, so the first thing we got to do is state the problem. So problem, we would like to test the claim that there are differences in mean or median weeks till death between the control group and the dosage groups. So then we need to run our test. We have, if we go out to red 40, we have, this is the data on A through D here. So don't pay attention to G or H yet. But this is the data from A, B, C, D. And it looks like we've got in one group 1, 2, 3, 4, 5, 6, 7, 8. We know from the central limit theorem that this may not be enough to ensure that means are, if we have evidence of high departure from normality, which it's going to be tough to test visually because we only have 8 observations, this may not be enough for the central limit theorem to make our test robust. This one clearly only has 10. This one looks like it has 11. Pretty low sample size. So the first thing we do is to go over here and put the data in what's called long form. So notice that we've restructured this data. Here it says control and all the control groups. When proc t-test, if that's what I run, or proc univariate or something else wants to have the treatment variable for all the observations and the time to death on all the observations here. So I've just changed the structure of our data, and I've brought it over here to SAS. You could do that in SAS or just do that in Excel and bring it over. So I've got treatment, and then I've got time, let's say. And so hopefully, stop me at any time, but hopefully that makes sense. And this is kind of the path I'd love you guys to take. There's more than one answer to this. But first of all, I have to know even what the data looks like. So I'm going to do a proc. First, I'm always going to do a proc print. And you might say, I don't have time to do a proc print. I only have 3 hours. I would almost say you don't have time not to do a proc print. Because if you end up trying to write a bunch of code and you actually haven't got the data in there, you're going to start debugging your code. You're going to start debugging your code thinking there's something wrong with your code when eventually you're going to go back and realize that the data never loaded. So I would take that extra 30 seconds to run that and make sure that the data is actually in there. And I would also clear the memory out of your computer so that it runs in some sort of timely fashion. I've got a lot of stuff open on this one, so this might end up not being, so maybe I don't want to run that. But anyhow, it looks like I've got the code. So then what I'd like to do is I'd like to plot the data. So proc univariate data equals, this would just be my flow, data equals red 40. And then I'd say by, or maybe I'd say class. Can I do a class statement in there? Actually, I'm going to do this.
I think it would be class, wouldn't it? By breaks it up into different groups. Class shows them all together.
You might be able to go either way. First, you're going to have to sort it. So sort data equals red 40. Proc sort by treatment. So by treatment run. And I think this should do it. And if not, then you just try and go around. So sometimes I don't have it all memorized, so there's different calls. So then, but I want to do histograms, and maybe I want to do QQ plots too, but histograms of time, right? And maybe I want to do a QQ plot too of time. That sounds great, so I'll run it. It's probably going to take a little while to run, unless there's an error. So I'll just kind of discuss, as it's running, Looks like there was an error. Well, as it's running, I'll kind of come back. I'll pretend it's like a cooking show. So in it goes to the oven, and out it comes right here. Voila. So I'll show you how to get this once it runs. But these are and these take a little bit of time. Notice that these are individual pictures that you can size. I really want to, highlight that. Please don't give me 14 pages with one histogram on each page. That actually is part of this is presentation. So that is almost grounds for some sort of deduction. You want to be able, when you get out into the world and actually produce these statistical reports, you want to you want to be trained to produce a report that somebody's going to take the time to read, that's not on, again, a big stack of 14 slices of paper, when you can put that on 3 by sizing these correctly. So all I did was put this in a table, however you want to do it, but I just simply put it in a table, and looks like a 3x4 table, and put those guys in there. I put the QQ plots, and I put the histograms, and I dropped the labels in there. So if I go back to SAS, that's where I got them from. So you can right-click on these and save them, right? Save picture as, or you can copy it, I think. Maybe you can't copy it. What I do is I just come over here, and I use this snipping tool. Very low tech, but I use the snipping tool and grab it, and I just do a screenshot and cut and paste that guy straight into my report.
You can click and drag the plots, can't you?
Out of SAS On Demand, you can. Maybe you can off of here. Depends on where you're going with them. I know that on SAS On Demand you can, though. Yeah. So
not on SAS On Demand.
What's that? Sorry?
Not on SAS On Demand. Like SAS On Demand, you cannot drag it.
Huh.
On the local machine copy you can, because I do it for my reports.
Okay. I thought I did it. I thought I'd done it from SAS On Demand before, but I'll check that out again. But this is the local copy, so you can just drag it off there too. However you want to get it done, that's your goal, is to make it nice and easy to read. And if you practice it a couple times, it's really easy. Same thing with these QQ plots. Just cut them out, paste them in there, and you can look at your histograms. Make sure that you make reference to all the assumptions, right? And you kind of phrase them in this way, or however you want to get the job done, but equal standard deviation. So in order to get that, I got these. So how do you get these box plots? You could run proc box plot, but so this was all for the normality, so you can read that if you have any questions. But all I basically said here was, this is small data. This is some evidence against normality. This is some evidence against normality. It's not a lot of evidence one way or the other, but it's such small data, I think I want to be conservative. And if I want to be conservative, I'm going to run a non-parametric test. I looked at these box plots, and it looks like there's some evidence of different standard deviations, right? These are small, and these are very wide. Again, it's small data. But the Brown and Forsyth test for my secondary evidence rejected. And since it rejected, I'm going to, what did I say here? Judging from the box plots above, there's strong visual evidence against equal standard deviation. Secondary evidence from the Brown-Forsyth test back that conclusion up. So I'm going to assume that the standard deviations are different, and that there's some reason to believe that I should be uncomfortable about the normality assumption. If I go back over here to my SAS, that plot, if you just run a proc GLM, data equals red 40, and then do, yes, your class treatment, and then do your model time equals treatment, and then do means. That's going to give you the means plot and that histograms. And then if you do, so means treatment, and then do / Hov test equals BF. That's how you get that Brown-Forsyth test. There's other things we can put in here, right? This is where we do the CL, the confidence limits. We can do some multiple comparisons. You can do some multiple comparisons, some confidence limits tests on the end of this, but this is all we want for this problem. I'm still checking my assumptions. So I run this guy, and I'll post this code. Again, put it in the oven, flip it back over. I'll pull that out in a second, but what we're going to get are these two plots and tables. Notice how nice and small they are, but still readable. Independence, for this, unless it's a paired t-test or a paired sample, you can assume independence. We'll get more into that next semester. And now we're ready to go. So if we were only concerned about the standard deviation assumption, we could run Welch's ANOVA, right? We could run that Welch's ANOVA because that takes care of, it makes it robust to the standard deviation, but we are not. However, we're not confident that the data come from normal distributions per the QQ plots and histograms. For this reason, a conservative approach, what's that? Sorry. Did somebody? Well, that's okay, cool. This is, so I'm just kind of flipping back over. This is the result of PROC GLM. There's the Brown and Forsyth test that I cut and paste, and that's my box plot. So you can grab those guys. And then, oh, I was back over here. So I decided not to run an ANOVA here, not even a Welch's ANOVA, because even Welch's ANOVA has the normality assumption. So, so what did I do here? So I said, okay, then let's run the alternative, the non-parametric alternative to an ANOVA, and that's the Kruskal-Wallis test. So this is your 6-step write-up. If you got any questions on that, let me know, but there's your null and alternative hypothesis. For this one, I didn't require the critical value. You could get that from an F distribution, actually from a chi-squared distribution. I won't require that for your ANOVAs, but you could grab it. Step 3, this is from the output, whoops. This is from the output of PROC NPAR one-way, which I'm about to run. So 9.756 and a p-value of 0.0207. That rejects this null hypothesis, and we conclude, so we reject, that there is sufficient evidence to suggest that at least one pair of medians, weeks till death, is different. So let's get that 0.0207. So you come back over here, we run PROC NPAR one-way, data equals red 40, and then don't forget the Wilcoxon. This is another place you could waste some time, is you're like, oh, why didn't it give me what I want? And you've got to put the Wilcoxon on the end of that. We're going to class it up with some treatment, and then our var here, this is very similar to the PROC t-test for a 2-sample test. The var is time, and that should give us our Kruskal-Wallis test by default. So we're going to run that guy, and then, so this is some stuff you'll do next semester, the PROC Genome Select. Very fancy stuff coming. Well, it seems like it runs fast when I come over here, so I'll come back over here. Wait, did it run? Oh, there it goes. So there's the Kruskal-Wallis test. So there's your 0.0207. There's your chi-squared test with 3 degrees of freedom. That's just another, chi-squared is just another distribution, like the F. It's actually related to the F and to the T. So you could look up that critical value, not required for us. We just know we're just comparing that p-value. P-value is smaller than 0.05. So we think that there is some evidence that there's sufficient evidence to think that at least one pair of these medians, but I don't know which pair. So we had to be clever in this one and say, well, if I don't know which pair, I'm not prepared to run t-tests. I can't run a Dinette's procedure or any other of those Tukey-Kramers. I can't even run a t-test because it's not based on the t theory, because I don't think that these are normally distributed, and I don't have enough data to think the means are normally distributed from the central limit theorem. So my original question is, we want to test the claim that there are different mean weeks to death between control and the dosage groups, which is kind of a Dinette situation, right? It's a control to each of the treatments. Well, there's only 3 treatments, and there's only one control. So that's going to be equivalent to simply running 3 rank sum tests. And to maybe Max's question, it is possible I would have you write 3 rank sum tests by hand. I'm just kidding. I wouldn't do that. I'm just kidding. But so in this case, of course, you would be able to use SAS. I wouldn't. You're not going to. You don't have to worry about doing excessive work with your hands. So anyway, that was mostly a joke. But here are our 3 rank sum tests, and those are. And this question came up last week. I would just run. Best thing you know to do right here is just 2 group rank sum tests. So I'm doing control versus low, control versus medium, and control versus high. Yes, we're losing some data. I wasn't able to ask that non-parametric guy what he thought about it. And the more I think about it, you don't know that distribution if you throw those other ones in there. So so again, we're just running it control versus low, control versus medium, and control versus high. Notice the low sample size is 11 and 9, or 11 and 8, and 11 and 10, because the control had 11 in it. This one goes to 11. So so how could you do something like that? You would just come back over here to proc in-par one way, and I would put a where clause in here, maybe that just said, you could go adapt the data. I think that might take a little bit of time. So where treatment let's see here, equals, so it's kind of the string version, EQ of what? Control and treatment equal to low. And I believe, I'm actually pretty sure that those, I mean, that is strict string. It's case sensitive in there. So whatever it is in your data set's what needs to be in there. So I'm about to see, it's almost worth going to look to make sure that it's capital, but I think it is. If I go to red 40, yeah, control and low and control are both capitalized, so I think I'm doing all right there. And then I run it. And you would do this for each, control medium, control high. And I'll flip out and come back to see the result of that. Uh-oh, looks like, I finally had an error. Aha! I messed up, right? It shouldn't be and, that should be an or. There are no groups that are control and low, so it gave me no data. The log is your friend, no data to analyze. So what I really meant there, I'll pretend I did that on purpose.
The pipe sign.
Was the or, exactly. So if you run that guy, and I'll let that go for a little while. Run that guy, we should get this guy right here. Notice that I just cut it out or dragged it over and shrunk it. I'll go ahead and say that now. It will not be a large deduction, but I think it's important enough to underline. If I have, if you turn in a sheet, or if a student turned in a sheet with like one of these tables on a sheet so that it looks something like this, and the only reason I bring this up is because it has happened before. Something like that would be a slight presentation deduction. If it took up more than half, I'll say that, if it takes up more than half the screen, there's, for one of these tables, that shouldn't be any larger what I have on here. So use your own discretion. If it's more than half the screen, I'll probably take a point off. If it's the whole screen, I'll really do it. So anyway, I just want to underline that. But this p-value here was 0.00, let's see, and you can use whatever one of these you want, whatever your preference is, the exact, t-approximation, or the normal. I'll just look at the two-sided. This guy is 0.0067. If I come back over here, there it is, 0.0067, Wilcoxon two-sample test. That is your rank sum test. Hooray. So after that, the only last thing that I really liked writing this question. The only thing after that I see is that we actually ran 3 tests. And I wouldn't blame you if you said we actually ran 4 tests, because we actually ran the Kruskal-Wallis test as well. I would take either one of those. It's a little tough because these tests are correlated. The Kruskal-Wallis test is what told us to look at these individual rank sum tests. So if you ran a Bonferroni with 4, k equals 4, or you ran a Bonferroni with k equals 3, either one of those is fine. That's what I should have done. So address the assumptions, no distributional assumptions. The data are clearly ordinal. The data can assume to be independent. We'll run those rank sum tests. So here was me. So on this one, you could have gone either way. I divided alpha by 0.03. So instead of multiplying the p-values by 3, which is totally fine, I divided alpha by 3, saw that that was 0.01667, and saw that this one is less than 0.01667, this one's less than 0.01667, and this one's less than, oh, that one's bigger than 0.01667. Oh, so I'm sorry, this is the only one. 0.0067 is the only one that's bigger, is the only one that's smaller than 0.0167 on these other 2. So it looks like control versus low is the only significant difference after a p-value change. Since I've written this, I've kind of changed the way I do these. It's much easier just to keep alpha the way it is and multiply the p-values times 3. I think it's easier. But you can either multiply the p-values times 3 or divide alpha by 3 and compare the p-value to that. So what did I find here? The Bonferroni correction was used. Therefore, interestingly, the low treatment group has significantly different medians than the control group. So the p-value, I used a different one, 0.0023, and from the normal approximation. So be sure you're kind of saying where you got that from. Note that the t-test approximation was used only the low group, or if the t-test approximation was used, only the low group would have been significantly different than the median. This analysis would have been okay as well. So I said in here that there's a couple of different ways that you could go. You could go like I did and do the rank sum test, do 3 individual rank sum tests. I think it's a stretch, but if you clearly stated up here that you think that this is not evidence against normality, I think that's a stretch. But if you said you don't think this is evidence against normality and you don't think it's far enough that the sample sizes should be good enough to get you out of, to make that test robust, it would really be tough. But if you really wrote it up well, I could see you defending a Dinette's test here. But remember, Dinette's test has the same assumptions. It's a modified t-test. So you've got to have these assumptions for the t-test in order to run it, which I think is a stretch. But if you wrote it up well, I'd give you credit for it. If you did not write it up like airtight, then there'd be some points, but it's not going to, if you perform the Dinette's test correctly, 6 steps with scope of inference and everything, there is tons of partial credit in these analysis questions. So don't get to thinking that there's one way to analyze it. There's a bunch of right ways, there's a few wrong ways, and there's a bunch of right ways to write it up, and there's a bunch of wrong ways and wrong conclusions to make. But that's it. So note, if you would have written the assumptions to defend and used the t-tools, the Dinette's test, that would have been an acceptable route. Okay, how was that?
Perfect. Thank you so much. I appreciate it, Dwayne.
Yeah, no
So
problem.
I think based on my understanding, like I think our previous conversation, we do median comparison only for the Kruskal-Wallis test or when we do a log transformation, correct?
Or a rank sum test, or the sign rank test for the non-parametric test.
Right. Okay.
But that's right.
Thank you.
That's right.
So to kind of segue off of that, on the review problem 2, you had on question number 4, it was there are four unique race categories with the HSB2 data set. You had on your solution, I think you ran a Welch's ANOVA for it, and I ran the Tukey's HSD, and got a pretty similar, I mean, it was the same answer, just I kind of got it a different way, and it had a little bit, like they had some slightly differing values, but it ended up kind of being the same. Is that a reasonable way to go about doing it, or should I have been thinking about the problem differently?
I don't have that one dialed up here. What was the question of interest for that one? I remember the HSB2 data set.
So it was there are 4 unique race categories. Test the first race has a different mean math score than the 4th race.
Okay. So you ran a Tukey-Kramer multiple comparison correction, and so if that is the question, that sounds to me like a, I'm sorry, well, the question was, it wasn't a particular race, if there was any differences in any of the races?
No, it wanted to see if there was, test to see if the first race has a different mean math score than the 4th race.
So that's a planned comparison, so you don't need a multiple comparison correction when you go in knowing that those are the 2 that you're going to, those are the 2 that you're going to test. So going in, if you're going to test 1 versus 4 or whatever the 2 you're going to go in, you could just run, that's a comparison K equals 1. And so you can just run one test on that. We don't need a multiple comparison correction. So what I should have done on that is run a Welch's first, depending on the assumptions, to see if there's any difference in any of the means. Right? That's what the ANOVA will do. A Welch's ANOVA will look, see, hey, is there any difference between any of the races? If that fails to reject, then I don't need to look any further. If that does reject, then I'll go and look at race 1 versus race 4. If I've made the assumption, dang, I wish I had that up right now. But we can just talk about it. If I made the assumption going in that all of the standard deviations of the races were the same, then I wouldn't even run Welch's ANOVA. I would just run an ANOVA. And if I can make the assumption that all the scores for each race were the same, then I would use all the data to estimate that difference. And I'm sorry, did I say, I said mean or median, right? Not just median? Or I said median?
I think you said both.
Yeah. So that just gives you the option of running a non-parametric test or a parametric test. So long story short, if there's no evidence against equal standard deviations, I would run a regular ANOVA. And then after that, I would run the contrast of race whatever versus race whatever, keeping the other ones in the model for better estimates of the standard error for higher degrees of freedom. I would not run just a basic t-test. However, we don't need to make our intervals wider, aka through a Bonferroni or a Tukey test, because there's only one comparison being made. I don't need to adjust for mean.
Right. I got you.
So I'd have to look at that because the answers in my mind shouldn't really be that close if you ran that. Because with 4 groups, there are 6 different tests. And so, so with K equals 6, that's probably a pretty significant difference in the confidence intervals. But if you want to send that over to me tomorrow, your solution, I can take a look at it. Probably won't take me very long to look at.
Yeah, sure.
Because, yeah, tomorrow's a great day, right? We can study a ton tomorrow, really kind of load it up, prepare for the big game, prepare like you're going into battle, whatever it is, get all your weapons together, and then we'll let it rip on Saturday. Basically, I need to so look out for tomorrow. I've been in contact with our head guy. There should be a proctoring service. And in this proctoring service, basically I'll give you a web page to go to, and they'll give you a bunch of instructions. It's the first time we've used them, so I apologize if it's a little rough. But actually, I'll probably end up giving you extra 10 minutes on the test. So you'll have 190 minutes instead of 180 minutes just in case. but they're going to ask you to show your ID, like up to your camera. They're going to ask you to take your camera, like your, whatever this is called, this laptop, and show it around and show that whatever's around. So I'm basically allowing you to have just about anything. The thing that you should not have out for the entire test, and I know there's emergencies and all of this, but what should not be out is your cell phone. So I hate, it's just I've been here before. So we'll just pretend the cell phone's kind of a distraction, so we'll just keep distractions out of our mind. But in that panoramic whatever, just there's, for 3 hours you can keep it on in case something happens. But if you have to take a phone call during the the middle of the test or whatever, that ends up getting flagged, and then that's just how more scrutinous. But basically, just so you know, it records your whole thing. They have a proctoring service that goes through and watches the whole video, and if something gets flagged, then they flag it and then tell SMU about it. Just because it gets flagged doesn't mean it's an infraction. It's just something abnormal happened. So, so obviously, I guess I don't know. It's the first time we've used it, so we'll see it. Everybody's on the honor code. We can trust everybody, so just realize that, and everything will be fine.
Professor, may I make a suggestion that if you have to take a call, put it on speakerphone. That way they could hear the conversation. That way, I mean, it's like, hey, you get your girlfriend calling, hey, honey, how you doing? It's like, hey, I'm taking an exam right now. As opposed to, hey, Alexandra, what's the answer to question number 2? I'm just stuck here. So I mean, the fact that they flagged it, if they could hear the conversation, they could see that it doesn't violate the honor code.
Right. I mean, I couldn't agree more. Even if you don't put it on speakerphone, if you just have your end of the conversation, and, unless somebody's developed some crazy code. I'm just getting crazy out there. So anyway, it's just a way to video it in an accountability way. And that way, when you guys move on and graduate, the next group comes through, that when they get out of the program, that they are as vetted as you are, that they have, that when you run into an SMU graduate of the MSDS program, that you have a candidate that knows the fundamentals of statistics, that knows SAS, that knows R. By the way, we're going to do a lot more R on the other side. So I'm revamping the homeworks for SAS and R. It's not a whole bunch of extra stuff, but it is, you will get experience in doing R in regression. So that SAS, R, you're well versed in these methods, and everybody knows what they're getting when they get an SMU graduate. And that's really what gets me pumped up too. So there's a lot of school pride now. So cool. Speaking of, I know I keep you guys over all the time, and you have every right to want to hold me here, but if you don't mind, I got a little bit of prep to do before I got the 8:30 to 10 6372 class. But does anybody have any more questions? If not, we can break out.
Just a quick one. If anybody wants to get together tomorrow evening to do a group study session, I'm available.
Awesome. Sweet.
Quick question. Headphones are okay during the exam, right? Like if you want to listen to music or something, wearing headphones during the exam isn't a problem, right?
That's a good question.
Yeah, when you got the phone call coming in saying that the answer number 2 is this, coming to the headphones, the proctor can't exactly hear that, right?
Yeah. So I mean, could we play can we play music on our computer? Like, do the proctors care if there's music blaring in the background?
Yeah, I think that's fine. Okay. Like music that's like out loud, I think is fine. And I really, I have to think about it. Probably earphones are fine too, but yeah, if you don't mind for this one, I mean, I think the proctor actually would appreciate the music. So, except so anyway. So yeah, so out loud's fine. Let me think about the earphone thing. I gotta process that. Maybe I'll be okay with that tomorrow. But yeah, for now, definitely out loud's fine.
Yeah, if tomorrow you could just like put up something on the wall of just like what you shouldn't do, that'd help a lot and clear up a lot of confusion.
Okay. Oh, on the wall. I thought you meant like
Yeah.
on the physical wall. Yeah. Okay. I'm not going to be there. Yeah, that's a good thing.
The exam is at what time? 1 o'clock on Central Standard Time?
No,
Saturday?
it should be
It's 11 to 2 Central.
Yeah, 11 to 2
11
Central on Saturday.
11 to 2.
It'll be too late if you come at 1 o'clock.
12 to 3 Eastern. That's what I'm looking at. All right.
Sweet. So yeah, and the good news is you'll be done with it in 3 hours. So that is, at the 3-hour mark, that's pretty good. There is a bonus. I won't let that one out of the bag, but you should look for that if you finish. And that's about all she wrote.
So you're going to post that that checklist and that code that you were working on?
Yes, I will do that right now.
Cool. Thank you.
Yeah.
And if we're not done with the test in 3 hours, it'll be done with us in 3 hours.
One way or the other, you've got the rest of the weekend. I'll get that. I'm going to just paste this code to the practice solution. So you just re-download that in a couple minutes, and you'll have that. But,
That Unit 7 is next week? The quiz and everything?
Yeah. Good question. So next week, what's this week? Yeah, next week is Unit 8. The next week is Unit 9. And then the next week is spring break. So you can use that week to catch up on stuff. So, catch up on family stuff or, whatever it is. So we've got this coming week. So we got this week, we've got this coming week, and we've got Unit 9. Everything's back to normal schedule. But where Unit 10 is, we're going to take a break and then pick up Unit 10 on the other one. So that week, I think it's like the week of March 13th.
So by next Thursday, we have to have Unit 7 quiz done.
Yeah, Unit 8 quiz done, but yes.
Unit 8 quiz? Okay.
What?
Yeah. So, and again, I don't want to let the cat out of the bag, but it was kind of planned that way. Unit 8 is really, there's no easy unit, but it's probably the easiest unit there is. It's just on basic linear correlation. So if you took the bridge course, or if it's just easing us into regression. So if you took the bridge course, or you remember from your intro to stat course, it's not intense like some of the later ones have been. So I think you'll find it pleasant. Cool. Alrighty. It's all right. I got to run. You guys got to run. I'll post that stuff, so check it out in a couple minutes. But who wants to whammo us out of here before the big exam? That is the question. Let's go with... Oh, wait. Oh. Dad's pointing to son. Son's pointing to John. Oh, yep, we got the Brady Bunch going. All right, it's moving up and down all around. All right.
Hollywood Squares.
Yeah, I like Robert's pointing at Joshua. Let's go with Joshua. I think he's got the juice this time.
All right. I got the juice every time. All right. 3, 2, 1.
Whoa!
Wow.
Ace that exam. Ace